Okay, we're going to have a look at proof now, which is the last two parts of the chapter. And we're going to sort of tackle this in one big video. Okay, so we're going to start by looking at types of proof. So we'll deal with a few here in year 12, and then we'll look at some other ideas in year 13 as well. So a proof is about being very, very pedantic, listing out all of your assumptions, okay, a clear set of steps, covering everything that can happen, okay. It also usually features a conclusion, which can be quite important for making sure you get all of the marks, okay. You need to be very, very critical of your working out as you go along, okay. It's not enough to just show that something is obvious or you think it was is going to happen. Yeah, you need to cover all of the bases. So first type that's visited in the book is proof by deduction. And this really here, you might have seen this quite a lot from GCSE. So let's have a look at a couple of examples. Prove that the product of two odd numbers is odd. So what do we need to do here? Well, we need to go back to this idea of sort of like 2n plus 1 as an odd number. But the thing that people are quite bad about at this is all they'll do is they'll say two odd numbers. Well, they'll say, oh, 2n plus 1 and another 2n plus 1. But the issue with that is they're the same number. So all you're doing is you're showing me an odd number squared. So actually that, if you wanted to show me, for example, an odd number and a different odd number, it would look something like this. What do we need to do? We need to show that it's odd. So here they use 2p plus 1 and 2q plus 1. It doesn't matter what your letters are. When we multiply them out, we get all of this here. Well, how do we prove that things are odd? We show that they are even, and then that we're adding or we're taking away an odd number. That's usually the way to do it. So you can see these parts here all have are all a multiple of 2. So you factorize that out. You do need to factorize it out just to make explicit what you are really showing. So two lots of something. So on the other words, on the left there, you have something that's even, and then you have plus 1 to it. So an even plus an odd is odd. Okay, and there they've got a bit of a conclusion as well that helps out. An identity. So identity we talked about earlier. Is something that holds true for all values of x, and you might now see from the factor theorem why we can put those 3 lines there. So prove that this is this. So what you want to do really is you want to generally start with the left hand side and show that you can work it to the right hand side. Okay, there's nothing really more interesting going on here. Okay. It is proof though, so what you must do when you are proving is you must make every single step, okay, nice and clear, step by step, no jumping ahead, please, okay, because the examiners are well aware of how good your calculators are, so you need to make it obvious that you understand what's going on and it's not just your calculator. Something else to be aware of is the way, sort of the direction of proof, I suppose, which is that you start from known facts. So, for example, you're allowed to assume that an odd plus an even is an odd. That's sort of an assumption about proof that's done here. And you need to end up to the conclusion. So you need to end up with what they're looking for. You can't go the other way around. Okay. You can't start with something that you are told to show as your basis, in other words, because that's what you're trying to prove. So what would be the point of doing that? Here's an example they give you. So it says, prove that if there are 3 consecutive integers, the way to do this, remember, is have like n and then n plus 1 and n plus 2. Yeah, these are 3 numbers in a row. They must be 3, 4, 5. So sometimes people will do something like this. They will start with 3, 4, 5, and they will show that it works. But, this is what we were trying to prove. So it's been done the wrong way around. What do we need to do? Well, we need to start with the consecutive numbers because it says if 3 consecutive numbers. So that's where we start, if 3 consecutive numbers. Yeah. And then we show that it works. we get 3 as x, then we get 3, 4, 5. Okay, that's the way around you need to work. So I'm just going to go over, let's just check. Yeah, I'm going to go over a couple very common ones because I think they come up quite a lot. So the first one we're going to do is prove that something is positive for all values of x. So in other words, this x squared graph never goes into this territory. It's always up here. So there's a couple of ways you could do this, especially when you learn differentiation later on. I'm going to show you from quadratics, though. One of the things that you did was completing the square. And completing the square will show me this minimum point, won't it? I know it's minimum because an x squared has this positive shape here. So if I can show that the minimum is above 0, then I will satisfy this. So I'm going to do x plus 2 squared. Okay. Minus 2 squared plus 5. So I keep this number off to the side and I complete the square on this part here. Okay, I will get x plus 2 squared. 2 squared is 4 minus 4, so it's plus 1. What does that mean? It means it has a minimum at minus 2, 1. So in other words, it can only go as low as 1. And because it's x squared, it would never go below. And that's it. Test your understanding. Prove that x squared minus x plus 7 is greater than 0 for all x. Compare with the top part above. Pause the video here. Have a quick go. Okay, so in other words, you were being asked to do exactly the same thing. Okay, so because the squared element is always greater than 0, we know that the expression is always greater than 0. Okay, so since the squared part is, well, I suppose it's always greater than or equal. If you had 2, remember, if you put 2 in here, this whole part would become 0. Yeah, this part here, but you're still adding 3 on. So the lowest that it can go is 3. Well, this part here that I did, the lowest it can go is 0. Okay, when you're at minus 2. So 1 is the lowest that it can go. It might be worth actually just explaining this a little bit more. What else is quite common? Something about like sums and differences with algebra is quite common. So prove that the sum of 3 consecutive even numbers is a multiple of 6. So an even number will be like 2n. Consecutive even numbers, we're talking about like 4, 6, 8. So what's the gap between them? Well, it's 2. So I could represent this as 2n, 2n plus 2, 2n plus 4. This is one way I could do it. And I'm saying one way here deliberately, okay? Because there are other ways you can do it. The sum, okay, well, the sum just means adding them together. So, you know, if I just add all of this together, I'm going to get 6n plus 6. Show that it's a multiple of 6. So what you want to do, that multiple thing, you want to bring it out the front of a bracket. Okay? And perfect, just like that. I'll show you another way you could have done it. So you could have also done, let's say, like, you might have done it like this. Sometimes it makes your proofs a little bit tidier for adding. So 2k minus 2, 2k, 2k plus 2. Well, if you add them all together, you'll get 6k. Okay, which also works because you've got 6 multiplied by k. So pause the video, have a go at the one at the bottom. Okay, so I'm assuming you've had a go at that one there. So the sum of the squares of 2 consecutive odd numbers. Okay, so I'm thinking something like this. is 2 more than a multiple of 8. So I want to show that this is 2 more than a multiple of 8. So this is kind of what we're looking for. We're looking to get this left-hand side to resemble something like this. Okay, they've gone for 2n minus 1 and 2n plus 1, which will sometimes, again, make your working a little bit tidier. Some stuff will cancel. They are consecutive, so because they're consecutive, they both have n. Okay, it's important that the same letter. And there we go, 8n squared plus 2. So I would write that as 8. I would probably write it like this. Okay, and plenty of questions to have a go at there. So let's just quickly visit the last few. So, you know, these ones are relatively straightforward. Proof by exhaustion. Proof by exhaustion means you look at all of the possible cases. So if perhaps the question was talking about dice, okay, well, it's 1 to 6, isn't it? So what you might need to do is you might need to do something with all of these numbers, and it might say prove that for all of the values on a die, and you would just work them out one by one and show that it doesn't work. So that's one sort of way that proof by exhaustion can come up, or it might be like show for the numbers between 1 and 10. Okay. Prove that n squared plus n is even for all integers. Well, here the clue is about integers. So what kind of integers can you have? Well, is even for all integers? Well, really, you can be talking here about even and odd. Those are your cases. So we can work through what happens in here if you have an even number and an odd number. So an even squared is an even multiplied by an even, which is even. And even plus an even is even. So it works. And, you know, you would write this out. Odd squared is going to be odd. And then odd plus odd will give you even. So you could represent it sort of like this. Now, in my opinion, this is perhaps a little bit redundant because n squared plus n is even. There's nothing stopping you from saying, well, if something is odd, I can just make it like 2k plus 1. You could just square that and then add it. And that will show you the result. And, you know, also for an even, you could do 2k squared plus 2k. So really, you can just use the deduction for questions like this, in my opinion. And the last one, counterexample. So this is very nice. Disproving, all you have to do is find a number where it doesn't work. A couple of hints for this one. It's normally good to use values like 0, 1, 2. 2 is good because it's the only even prime number. Some kind of negative numbers are good as well. And also the number itself that's being talked about or that you can see. If you use these, this is a quick way to sort of find normally when a rule doesn't work. You know, let's put -1 there or something. So disprove the statement n squared minus n plus 41 is prime for all integers. So you need to find a case where it's not prime. And you can play around with a few. Well, 0 is 41, so that's still prime. It doesn't work. 1 squared is 1 minus 1. That will be the same as the 0, so that doesn't work. 2 squared is 4. 4 minus 2 is 2. 43, that doesn't work, so it's not looking great here. -1, that will give you 1 minus 1. So that also sort of, that's not great. What about 41? 41 squared is, I don't know, a big number. But take away 41 and add 41. Those cancel each other out. So you'll be left with a square number. So if you have n equals 41, 41 squared is definitely not prime because 41 is a factor at least. So, you know, that takes a bit longer, that one. My advice would be to use these as a shortcut to find when it won't work. Okay, and that's the end of the chapter.